Okay, we're continuing to work with permutation problems that do not have all distinct objects, but these are permutations with repeats. And we're going to solve them using the formula that we developed in previous videos, and also to solve the problem using a combination approach. And here's the problem. An investment club has received 15 requests regarding new inquiries. We want to know how can these 15 inquiries be divided among the 3 founding officers, so the freshman officer receives 7 of the inquiries, the next most senior officer receives 5 of them, and the most senior officer receives 3 of the inquiries. And the way to approach the problem perhaps would be to imagine that each one of the 15 requests, each one of the 15 inquiries is put into an envelope like this. And if we're asking them how many ways can we choose 7 of them for the freshman officer, how many ways can we choose 5 of them for the next most senior officer, how many ways can we choose these envelopes for the 3 of them for the most senior officer, that's tantamount to asking, well, how many ways then can we permute these 15 different envelopes if we consider 7 of them to be identical. So we consider as 15 total envelopes. But here then, since 7 of them are going to one location, we'll consider them as 7 of them as identical. Because they're all targeted for just one person. Likewise, there's another group of 5 of them that we consider as alike. And finally, 3 of them that we can consider as being the same, because they're all targeted for the same destination. So the number of ways then that we can permute these 15 different envelopes with the restriction that 7 of them are identical, another group of 5 of them that will be identical, another group of 3 of them that will be identical, and that would of course be 15 factorial divided by 7 factorial times 5 factorial times 3 factorial. And that would tell us the number of ways that we could distribute these 15 envelopes or these 15 inquiries. So 7 of them go to one destination, freshman officer, 5 of them go to another destination, the next most senior officer, and 3 of them go to a third location, the most senior officer, by considering 7 of them to be identical, another group of 5 to be identical, and another group of 3 to be identical. Now, there's another way that we can approach the same problem, and that is from the combination point of view. Again, we have 15 envelopes here. The order of them is irrelevant. It's just a matter of having different envelopes. So we can ask ourselves, well, out of these 15 envelopes, how many different ways can we select 7 of them so that the order doesn't matter? We know what that is. That's this. Now, so that would be task T1. Task T1 is selecting the first 7 of the envelopes. Task T2 will then be to select the next 5 envelopes. Now here, how many ways can we do that? Well, we got 15. We already selected 7 away, so there are 8 left that we can choose our 5 from. So that would be the number of ways that we could perform task T2. Task T3 is to select 3 envelopes or 3 inquiries for the most senior officer. Here there's only going to be 3 left over, so the one way that we can do it. We already used up 12, so we have 3 left, and we're going to choose 3 of them. There's only one way that can be done. Or if we want to look at this more formally, you can see this is equal to 3 factorial divided by 3 minus 3 factorial, which is 0 factorial, times 3 factorial. That's 1, and we explained in a different video, a previous video, that 0 factorial, that's 1. So this is just 1. So the total number of ways that we can perform tasks T1, T2, T3 by the counting principle, that's equal to the total number of ways that we can perform task T1 times the total number of ways that we can perform task T2 times the total number of ways that we can perform task T3, and that's just 1. So it's going to be this times this. So let's see. Here we have, this is equal to 15 factorial divided by 15 minus 7 is 8 factorial times 7 factorial, and this is 8 factorial divided by 8 minus 5 is 3 factorial times 5 factorial. And here these cancel, so this comes up to be equal to 15 factorial divided by 7 factorial times 5 factorial times 3 factorial. That's the answer we get using the combination approach, which was exactly the same answer that we obtained using the permutation approach with repeats. Either way, we get the same expression. So, okay, that's it for this video. Again, we wanted to try to show you another application of permutation with repeats type problems, how we can handle these using our formula that we developed in previous videos, or how we can solve the same problem, thinking of it a little bit differently, how we can also solve it using the combination approach. Now, I might take the time here to alert you that we have many different videos that we've posted here with permutation problems and combination problems. We're trying to do it in a certain order so that hopefully it makes sense to you. But if you found this on YouTube, you may not see the videos presented in their proper order. They might be kind of scattered all over. So if you go to the website, digital-university.org, and you look under the combination permutation videos, there they'll be all presented for you in their proper sequence. Also, at the website, there are hundreds more problem-solving videos in different types of subject matter that they might be useful to you as well. Okay, anyway, that's it for this video. Come back and join us for some more videos. We'll try and solve some more